Hello everyone, very good morning to all the students present in today's lecture of digital communication. So today we start from different topics related to digital communication, and also we are going to see a few numericals which would be helpful for you to better understand some of the theoretical concepts. So let me share my screen. Is the screen visible?
Yes.
Okay, thank you for the response. So a few very simple numericals we'll quickly go through, and then we'll take it our presentation. Okay, so the first question will take with this regards to Nyquist criteria. Sorry. So suppose some signal function is given to you and you are being asked about the Nyquist rate or Nyquist interval, how you should take. Okay, so the question is, find the Nyquist rate and Nyquist interval for the signal represented by as. So the function is mt equal to 5 cos 1000 pi t cos 4000 pi t. Okay, this is the signal given to you, and you are supposed to find out the Nyquist rate and the Nyquist interval. So whenever such form of signal will come, you have to transform it using trigonometric formulas, cos A, cos B, cos A minus B, when you expand like that. So this is now in multiplicative form, so you need to transform it. Okay, and why we are doing, because we want to have additive components in our signal equation. Okay, then we will find the maximum frequency which will be there in our signal. Okay, are we good? Is my voice properly audible?
Yes, sir.
Yes, sir.
Okay, okay. So the same mt we can write using trigonometric formula as 2.5 cos 3000 pi t plus cos 5000 pi t. This. Okay, I think this is very simple, clear to you, Hana? Cos A minus B, cos A plus B. Okay, so you have components as, so this will come if you separate it, so it will be 2.5 cos 3000 pi t plus 2.5 cos 5000 pi t. Okay, so this is t. Okay, this is t. Now this essentially it is, when you compare with the formula omega t, omega is 2 pi ft. So pi is given, so this your 2f will be 5000. Here 2f will be 3000. So our mt we can say is band limited to how much frequency? maximum frequency FM as how much? This is 2F. So FM will be 2500 hertz. Okay. So this will be our signal is band limited to maximum frequency 2500 hertz. Hence, what will be the Nyquist rate? Will be how much? We are not considering this because half of this is 1500 hertz. So obviously maximum we have to take. So we are taking 2500 hertz, not the 1500 hertz. The Nyquist rate will be 5000 hertz. Okay. And the Nyquist interval is just the reciprocal of this. Nyquist interval is 1/5000 in seconds. Okay, so this will come around 0.2 millisecond. Very simple question. Is it okay? Everyone clear with it? Please, can anyone confirm?
Yes, sir.
Okay, thank you. Now, next is I just change some values. That's it. That will be our second question. So second is your MT is given as 10 cos 2000 pi t cos 8000 pi t. 10 cos 2000 pi t and cos 8000 pi t. So please everyone tell me what will be the Nyquist rate and Nyquist interval. Please. Let's have 1 minute, 30 seconds or 1 minute of time. You can quickly find out. So first is maximum frequency, how much it is coming, and then the sampling rate, which is twice of FM. How much is this?
FM equal to 5000.
5000. Very good. So 5 kilohertz will be your FM. So FS will be your 10 kilohertz. Okay. And just the reverse of this would be your Nyquist interval. Okay, so these are a few simple questions. Now, next is related to line coding. Okay, so consider the binary sequence 01 0 0 101. Draw the waveforms for following signaling formats. So you have to represent this graphically in unipolar NRZ, bipolar RZ, and AMI RZ. So again, I give you 1 to 1.5 minutes of time, and Meanwhile, I just draw the axis, and then you people can tell me how the waveform will look like. So please take a pen, paper, and just use these three formats to represent this binary sequence 0 1 0 0 1 0 1. Okay, this you have to consider. Zero 1 0 0. Three more intervals we require. So this is for 1, this is for 0, and this is for the last bit, like this. The first one is your unipolar in our set, bipolar R set, and alternate mark inversion return to 0. This is R set. Anyone? So first start with unipolar and R set. So what should be here in this duration? So let me write our sequence bit 0 1 0 0 1 0 1. Okay. Now please tell me, for unipolar and R set, what should I draw in this duration? Negative or 0?
0.
0. Okay. So 0, because it is unipolar, it is 0. Okay. Then 1 is simply your high voltage. Then again 0 0, then 1, then again 0, and then 1. I hope this is pretty simple and clear to you. Everyone okay with this unipolar NRZ? Very simple. Yes or no?
Yes, sir.
Okay. Next is your bipolar RZ. So first thing is bipolar. So two polarities are there. First thing. Second thing is it is returning to 0. And we know the rules of returning in the exact middle of the time duration. It returns to the 0 axis. Okay. So 0 we represent using negative polarity. So half duration, and then it returns to 0. This is 0. Then is your 1. 1 is represented by positive polarity, but it returns to 0 in exact middle. Okay. Then it comes here and returns to 0. So this is half. Okay. So I have done, let me erase it so that you do not get confused. Yeah, this is middle one. So 0, then again it will go negative, and then like this. Okay. Now it will take positive, return to half, then go like this, For 0 it will be negative, return to 0, and then your final bit 1 like this. So this will be your bipolar RZ. I hope it is also clear, everyone.
Yes, sir.
Okay. Last is your alternate mark inversion, return to 0. So alternate, what is alternate in AMI? Alternate is the successive ones which are coming, they will be using alternate polarities for their representation. So first, suppose at this instant one comes, so we are using, say for example, positive polarity. Whenever the next one will come, no matter how many 0 comes in between, the polarity which will be considered for the next one will be alternate of it, means the negative of it. So since it is returned to 0, we also have to take care of that RZ portion. So in exact mid time, it will come here, and entire till this point, till the next one comes, it will be 0. When the next one comes, you have alternate polarity. So previously it was positive, it will be negative this time, like this. Okay, and when next one is coming here, so here it will be like this. So this will be AMI RZ. Are we good?
Yes, sir.
Okay, we are good. So similar questions you may be asked in your evaluation. So better is you practice with few sequences. There are lots of online tools which are available. You just input the binary sequence and they will generate the signaling line codes for you, graph for you. You can just first draw your own interpretation of the binary sequence in the signaling format, and then you can compare with the results. So it will give you a little practice. It will save time whenever you are evaluated. Okay. I'll try to share those links with you people so you can have a look at it. Okay, so let me reshare my screen now to our presentation. Okay, is the screen visible?
Yes.
Okay, thank you. So we have seen earlier non-uniform quantization and compounding. We'll just quickly go through non-uniform quantization. Why we do? Because of this very nature of the signal like this, and we have already seen this. And we use compressor and expander, and we collectively call it as, so compressing and expanding we are calling as compounding. So that is compounding. Whenever you hear the word, it is related to non-uniform quantization. Okay, so you have to relate terms like this. So I'll share this PPT with you people. You can like this. Then we have seen certain compounding laws, mu law, A law. We have seen they are followed in different parts of the world. Mu law in US, in European it is A law, and the equations they are also given in front of you. Okay, so what I will do, I will share this PPT and would advise you all to go through this numerical, very simple, and just have a clear understanding of this graph. If you face any problem, we will discuss definitely. So, but I am as of now giving you people as a task to just look at it. These formulas we have seen in earlier lecture, and we need to remember those formulas. This is similarly for A law. PCM, transmitter, receiver, and line coding. So this is the baseband transmission and reception for pulse coded modulation, pulse code modulation. So you can see GT and then NT aliasing filter, then you have a compressor, then this entire thing is for A to D conversion. SH we represent the sample and hold as SH, then you have quantizer and then encoding, and there you are getting the signal. The signal you are transmitting over channel and then you are receiving here. Okay. Now, what is the purpose of repeater? Can someone tell? You can see in this channel portion, this channel is written, so this is actually channel. What is this regenerative repeater? Anyone would like to give a try? Am I audible?
Hello.
Yes, please tell.
Sir, we can use the repeater for increasing the length of the wave.
Length.
Length of
So, length or height?
the height in the sense.
Okay. And length also?
That I don't know, sir. Sorry.
Okay. Okay. So good. You have tried. Good. The thing is, you have to remember distortion should not happen. If distortion happens, there is a loss of information. But in certain channels, you have distortion also. For example, in fiber optics, the signal is in which domain? It is in light domain. Okay, the wavelength, the frequency of the signal is such that it is falling into light domain. Okay, sometimes visible, sometimes different domain. One second. So when the signal is transmitted over the channel, in this case example, say it is a fiber optics, because of the nature of the channel, the signal, at after long distance, it changes its shape. That is distortion. So if I show you two graphs, one is this was the actually transmitted signal. Say this is level 1, 0, -1. Say at one point you are having this signal where this is say 0.5 and this is minus 0.5. Okay, like this, and you have another signal which is like this. What do you people say? Which signal is in? Suppose this level is 0.8. This is 0 minus 0.8 volts. Now you people tell which signal is in better condition.
First signal 1 to -1.
No, this is the original signal when we transmitted it. Okay, at the transmitting side.
Second one, 0.5 to minus.
Yes, and can you tell why? What can be the reason for so? Because the shape of the signal is retained in this graph as visible from ZC. What is ZC?
Sir,
Zero
phase
crossing.
change.
Yes. So phase change means the zero crossing actually deviates from its normal position. But in this case, though the signal level is less, becomes uh, it decreases, but it passes from the same zero crossing points. Whereas in this case, it is not the so. It is passing at different points, or it may expand also like this. If some signal do like this, so z crossing, zero crossing is change, means there is a distortion, there is a change in the shape of the signal, and change in shape is not good because we do not know exactly when the phase reversal happened in time, so we lose this information and it is not good. Attenuation is okay, it is tolerable. We can use regenerative repeaters to get the original or the high level signal back again. We can use amplifier to take it this zero point 0.5 level to 1 level again. That is doable, but to undo the change in the zero crossings, it's very difficult. So regenerative repeaters, they sort of retain the zero crossings, only amplify the amplitude which gets decreased with as the signal travels over the channel. But you may question, if suppose distortion comes, how to take care of it? Can somebody say, if distortion comes, how we can take care of it? Is there any way to get rid of distortion? So for that, you have to understand what is the reason of distortion. So the prime reason for distortion is the channel characteristics, right? If you understand the channel characteristics properly, you can undo the effect of distortion by applying the inverse system transform, inverse system response. If the channel is introducing distortion with a certain model, just inverse of that model if you apply, it will try to undo the effects of distortion. I hope you all are firm with system response H, represented by H. Yes or no? Capital H. Or in time domain it is small h, like Hn. Systems are represented by their system response, system model. So this is Hn. Everyone agrees with this?
Yes, sir.
Or in continuous time domain it is Ht. Okay. So if you are able to identify the impulse response or the system response of the system means channel in this case, you can undo it by applying the inverse, by feeding the signal to the inverse of the your system response. But still there will be few losses, and one must have to um, take care that distortion does not happen. Like for example, in fiber optics as channel, uh, there is something we call as dispersion. Dispersion happens. Okay, it is a very common physical term, dispersion. So because of dispersion, what happens? Your the actual signal it gets spread out. So if actual signal was like this, it gets spread out like this. Okay, because of the dispersion. Because what happens? Different wavelength of light travels with different speeds in the fiber optics. So we undo it by using some kind of mechanism which will be the exactly reverse of this impact. So how we can do that? Like fiber optics, we have having a model which is transforming this to this, which is happening. We want to undo it. So we will undo it by using a small length of fiber optics whose system response is exactly the inverse of the fiber optics which was there in this channel. So we will say after 2 kilometers of fiber optics, we will use say 1 meter of a piece of fiber optic which is having a different text will. Hello, am I audible?
Yes, sir.
Okay, one phone call came in between, so got lost the connection. Okay, so I hope it is clear. So we need regenerative repeaters majority of times to tackle the problem of attenuation. We get the healthy signal again, and certain cases we want to get rid of distortion also. Though we will cover all these aspects later on. And then we are generating using pulse detector and then shaping, because the signal will be like this, little attenuation, selective attenuation will also take place. We want to have this kind of signal exactly. For the signaling format. Okay, sorry for interruption. And then we are doing the back conversion, digital to analog conversion, using reconstruction filter and then amplitude and then expander. Because we have used the compressor here, we have to use decompressor in the last. Sources of corruption in pulse code modulation. Quantization noise, we are aware of. Overload noise, and we know timing jitter. So it is something related to timing error caused by a shift in the sampling position. So when we are sampling, if there is a little shift in the sampling instance, we will have, we call as timing jitter. For that in fact has not to be there, means there should not be any shift in the sampling time instance. That can be done with stable clock reference. Stable clock reference, how we can get? By getting best quality oscillators. Crystal oscillator are the best in their performance. And you have channel effects like attenuation, inter-symbol interference, ISI. So if you transmitted the signal like this, suppose, and because of the channel properties, the signal got spread like this. This one also got spread like this. This one also got spread like this. So you can see the overall signal will be like this. So it is like kind of pulse broadening, and this signal might interfere in the resemblance of the 0 bit at this point, which is not good. So that is we are calling as inter-symbol interference. Say this is 1 0 1 0 1. If because of this pulse broadening, because of increase in amplitude, if one is interpreted here, it is kind of ISI. It is because of two symbols spreading, you have different symbol being interpreted. So that is not good. That is happening because of interference. Sorry. Then you have noise impact. Noise, whenever comes, we represent it as AWGN. Has anyone uh, seen this term earlier also, AWGN?
Yes.
Please, can you tell something about it?
It's additive white Gaussian noise.
Okay.
And it is basically a number of frequencies which have the same amplitude throughout the transmission.
Good. So wide means it is expected to cover a wide range of frequency, very, very large bandwidth. So any large bandwidth noise which is distributed as per your Gaussian distribution curve is actually additive white Gaussian noise. So the majority of the noise which is encountered in communication is actually AWGN. So now the strength of that AWGN definitely varies with the ambience or the environment of the channel, but it is the prime source of your noise addition to the original signal. So we need to model. So whenever these communication infrastructure is installed, whatever medium is there, for example, the channel is modeled, the channel noise impact is modeled with the help of criteria such as whether the area is urban or rural, whether the area has vegetation or any kind of hills, mountains, whether the area is having high humidity, etc. All these parameters, they are considered to model the channel characteristics and then impact of noise. So similar counter actions are taken to nullify the impact of AWGN, the addition of noise. So we will see these topics in detail whenever a specific modulation scheme and channel selection will come into further units. Okay. And then is your synchronization. So synchronization, because we are sampling at a particular rate, we are using some crystal oscillator. So at the transmitter, whatever frequency you are using, and same frequency you have to use at the receiving side. Otherwise, there will be problem of non-synchronization, asynchronization. So the received signal must have to contain information about the transmitted clock. What signal you are receiving, it should have a signal period in between where the information related the signal frequency at the transmitter is contained. If you lack this, you will have erroneous reception. Your transmitted at F1 trying to receive with F2, it will be leading to totally different signal interpretation. These are few of the sources of corruption in pulse code modulation. Are we good, students? Everyone is able to understand, or any doubt is there? Please give a response. Am I audible?
Yes, sir, you're audible.
And understood also? Please tell na. If there is any problem, we can discuss. Or let me interact with you people. I think that has to be there. Adit Patel, can you listen?
Yes, sir.
Any difficulty in understanding?
No, sir.
You are okay with the? Okay. Chirag Suthar,
Yes, sir.
any difficulty, any problem?
In the subject, no.
Whatever we are going through the topics, I hope they are clear to you. Is it?
Yes, sir.
Okay. Thank you for the response. Nachiket Soni,
Yes, sir.
everything fine?
Yes, sir.
Okay. So line coding and alternate modulation. We'll see line coding we have seen. I'm not going to repeat it again. Just this different material I have prepared. Then so you will find few additional this thing phase encoded, which you can quickly go through, and you can easily understand the phase encoding for the line signaling format, like biphase level L, M, and S. Okay, and all these are explained here. So I suggest you people to just take this example, understand very plain language it is written. If you people face any problem, we will discuss in the next lecture. Okay, so please go through it. Very simple. If you have understood the line codings earlier, NRZ, RZ, AMI, bipolar, unipolar, this will be also very simple. And these are the representations of electrical parameters. Unipolar one is some plus A. A can be 5, 1, 3.3 volts, etc. 0 is 0 volt. Polar signaling, you have 1 as positive polarity plus A volt, 0 as negative polarity. Bipolar, you have 1 as A and minus A and 0 as 0 volt. Okay, AMI if you remember. So one we are representing using both plus as well as minus voltage, minus negative polarity. Manchester we have seen one is plus polarity signal, half duration followed by minus A. 0 first negative polarity will come and then positive polarity come for half of duration. So combinations of all these will lead to different line coding signaling formats. And this example also I have included. Now, what is the time? In take 2-3 slides also. So PCM you have understood. Everyone understood PCM, pulse code modulation. We take samples, then we quantize, then we encode. That is the same pulse code modulation. Delta modulation we have seen is a specific scheme where we were representing individual step size increments delta with either 1 or 0 depending on whether step size has increased or step size has decreased. That is delta modulation. Adaptive delta modulation, it is a variation of delta modulation where the increment or decrement in the step size is not fixed. It is not delta or minus delta, but it varies from how much amount of change has happened in the signal. So now we take differential PCM, and next is your differential PCM. So when you are sending the signal in the PCM format, so at you can see different time instants, TS, 2TS, 3TS, you are having a fixed width, time width signal, and that level in that particular duration denotes the signal level at each quantized level. So if the signal level is this, it will be 0, 1, 0. If the signal level is this, 1, 0, 0, 1, 0, 1, like that. And for this duration, it will be there. This is normal PCM. In DPCM, we try to remove the redundancy portion of this. Where is the redundant information in PCM? The successive samples, they are highly correlated. This is highly correlated with this. This is highly correlated with this. Similarly, so all the present samples, they are highly correlated with their previous samples. This value is achieved on the basis of this past value. Means there is some correlation in between. So values from present sample to next sample does not vary in large amount. If you look the increment in the signal level from this level to this level with respect to this level, there is not a big increment. Here also it is a very small increment is there. Here you can see very small differences there. So the adjacent samples of signal carry essentially same information with only little difference. Hence, when such samples are encoded using simple PCM, they contain high redundancy. Means something is there, some information is there which we can get rid of. Okay, because relatively there is not much increase or not much decrease, except only in the case where a signal is highly transient, highly unpredictable. Okay, increasing or decreasing in unexpected magnitudes. So if there is a way to get rid of this redundancy, the overall bit rate what we require will decrease. So if the bit rate decrease, the number of bits which we require to transmit one sample will also be reduced. This is we call as differential PCM. Differential comes from the word difference. So difference between current and the past value, past sample. If we transmit only the difference, we call as differential PCM. So the DPCM transmitter actually it works on the principle of prediction. How? The values of your present sample is predicted from the past samples. So you have something we call as prediction filter system. Now this prediction has to be definitely very good, and this is very close to your actual sample value. Okay, so if you look at this is a differential PCM. I hope the screen is properly visible. Okay, so this is your input signal. Here you are comparing with a reference signal, which is actually the output of a prediction filter. This is the quantizer. So every point of this system you have notation for all the signal components. So suppose your sampled signal is represented x and ts, predicted signal is x cap and ts. Who is predicting? What circuit is predicting? A prediction filter. It is a specific circuit. So the error signal between the predicted. So definitely it all depends on the accuracy with which the signal is predicted. If it is good, you have a very good DPCM transmitted signal. If this is not good performing, predictions are not that much good, you will have problems with the transmission. So this ENTS, which is nothing but the difference between your sampled input x and ts and the predicted value x cap and ts. We get this, we expect this. What is the difference? That is the error. That is actually error in between the prediction and the actual value. So we are using this error ENTS to further quantize. So you can see ENTS, which is the difference between x and ts and x cap and ts. We are quantizing the signal in EQ and ts, and then we are encoding the same error difference into DPCM signal. Okay, you can see this EQ and ts we are taking here, and this x cap and ts also we are taking here to feed it into the input of prediction filter. Can someone tell what is this? What is this principle? You might have seen in signal system. This is known as feedback. So this is the feedback. This is the feedback for the prediction filter, and this is the feedback for this entire DPCM system. Are we good? Rahib Patel,
Yes, sir.
are we good?
Yes, sir.
Okay. So this quantized version, your sampling here is forming part of these feedback loops. So feedback, if you remember, is for stability control. Okay, so we are utilizing in that sense here. Quantizer output EQ and TS, which you can see here, is one is ENTS, what gives its input, and the QNTS, what quantizer does with the received signal. Sometimes it will quantize, no, if the value is 0.3, it will assign it to the next level, or depending on nearness to the quantized level, it will add some component or subtract some component. So plus QNTS. This is whatever is added to reach the, or subtracted to reach the nearest quantization level. XQNTS, which is the input to the prediction filter. You can see what is going into it. X cap NTS. This X cap NTS, which is the output of prediction filter. So this is feedback. Whatever output of prediction filter, take sample of that also, and then add your EQNTS, means quantized error output. Add these two. So input XQNTS for the prediction filter is the predicted output plus EQNTS, which is the quantized error signal. And when you perform this simple equation solving, you will get XQNTS equal to XNTS, this one, plus QNTS. So what we can say is the quantized version of the signal XQNTS is the sum of original sample value and the quantization error QNTS. Okay, so we can make use of this quantized error signal to encode it and then transmit the signal further. So with this, we take a pause at this point and we'll continue discussing differential PCM. So one thing has to be clear, PCM is simple sampling, quantization, encoding, that's it. Differential PCM, why we do? Because relatively the successive values, they are highly correlated. Okay, the increment or decrement definitely with reference to certain amount from the past value. So what we are doing, we are trying to leverage out that correlation. We are trying to use, okay, this much have increment have taken place, this much have decreased. So we are using this difference in the samples as an error signal, and then we are transmitting that signal. So how do we do that? We do with the help of a prediction filter. Okay, so we'll take this DPCM further in the next lecture. So if you have any doubts or any queries, just discuss, or meanwhile I take attendance. Aryan Pandya. Aman Narayan. I hope you guys are there. Dev Satapara. Harsh Patel. देखिए, if I am calling your name, please respond. Jeel Jain. Janil Kundalia.
Hello. Yes, sir.
Okay, who is this? Everything is clear? You are
Yes.
able to understand? You are able to understand?
Yes, sir.
Okay. Kshitij Surana. Manan Mehta. Nachiket, Soni.
Yes, sir.
Okay, everything fine? You are able to
Yes.
understand?
Yes, sir. I'm able to.
Because it is very important. Suddenly, what will happen? A rush of topics will come based on these concepts. Okay,
Yes, sir.
then
We
we
quite
will.
of like we little bit experienced that in DSP as well. So
Okay. Sorry, can you say it again? I could not listen.
I was saying we have experienced it a little bit in DSP. So
In the last semester?
uh, digital signal processing, sir.
In the last semester or current
Yeah,
semester?
in the last semester.
Okay. So I think most of the nomenclature you are easily correlating.
Yeah.
Thank you, Nachiket. Okay, then if no further queries, thank you everyone.